What's up, Joe Gamers? Today we're gonna be talking about planes, not 9/11 planes, but the planes in math and graphing. So in my last video I talked about lines pretty badly, I'm not gonna lie. Replace this X, Y, Z and Y and in R cubed. So in the real third dimension, this is what we have, right? And a plane would just be an extension of a line. So we had a line like this. Say this is a line and you want to make it a plane. The plane would just look like a square, like infinitely stretching square, like so. This is what a line would probably look like, yeah. So this is what a line looks like, or a plane, I mean. This is what a plane would look like. Just a really flat, thin sheet. If I can rotate this, you would see that when I move it to some plane, you'll see it only as a line like this, like I'm referring to this part right here. You rotate it to the, I'd say the ZY plane. Rotate it only to the ZY plane where you're facing directly at the X direction. You'd only see this straight line, but then zoom out a bit and you'll see the full distance or whatever of the plane. It's as thin as a line, but it still extends to X, but has like a very thin thickness. And how you make a plane is not what you'd think of how you'd make a line. So when I said earlier about lines, I said you needed a point, or at least, yeah, RO as your point, and then a parallel vector. And some of you might think, well, if a plane is just an extension of a line, but going in a different direction, we just find a parallel vector for that plane and then extend it, right? Well, it's not that easy to just say that. In fact, you need at least 2 vectors to define your plane. It's not at least 2, it's at least 1, but it's not what you think. So the reason why you need 2 is because a plane could be as flat as this, and you'd say, well, it only goes in this one direction, so I can define it like this, and this would probably be Y, or actually, what could this be? I think this could just be X was X equals, I don't even know anymore. Or is it actually Y? I think it's actually just Y equal, wait no, it's Z, my bad. It's Z equals whatever number this is. Z equals whatever, some number. And then it just extends outwards in this XY plane. And you'll say, well, I have a parallel vector that is 0, 0, N, and you say, well, I can define it with only this one vector, and you might be right on that, but yeah, remember that there is another thing right here. So let's say I drew a vector that was exactly pointed here where it's going, right? Well, you could make a line out of this for sure, yeah, but there are lines that are parallel to each other, I mean not parallel, but they'll never intersect, called skew lines. And the reason why these skew lines exist is because they are in different planes, but those planes themselves are parallel to each other. So you can definitely define a line with one vector, because that one vector will correspond to that one plane line, a line on a single plane with the same slope. But a plane cannot be defined with just one straight vector like this, because it has another direction over here where it extends. This vector does not define how it extends. For all I know, or all you can know, that the plane could also look like this, and it's still going in parallel direction of this, but now the other vector is right here. Or it could be like this, perpendicular to this plane. You wouldn't know which direction it's going, so you need another vector to define the other direction. But why am I talking about this? I could have just said this in the first place, but there's actually an easier way to use it with one vector. So I said that say this plane can hold many lines that intersect with itself, but there could be a parallel plane that may have the same line or even intersecting lines if we place those two planes side by together, but they don't ever intersect because they're on different planes. Now, the reason for this, the way to get your specific plane, so you know that where your lines lay, come from two defining vectors that make up your plane, which is, let's call it V1, and let's call it like right here that plane, but also the plane that looks over here. So it's basically like two lines intersecting, and then you color in the directions. That's what two lines are, and we're gonna call those two vectors V1 and V2, and we're gonna do the cross product of these two vectors, so we get one unique vector, let's call it V3, such that it has the information that both these vectors have, but it is unique to those two vectors themselves, such that you can define a plane with just one vector, which is the cross product between two vectors. Yeah. So instead of defining as these two vectors, we can define it by its cross product that is perpendicular and goes up, and we can use a point on any point on this on this plane. We can use the vector and a point, because remember, we can have parallel planes, so we need a specific point such that we know exactly which plane we're using or we're defining. So any point here works. We just gotta connect the two, and then the vector form of a plane is, let me see, I haven't used it in a while. Can't find it. Okay, it's N times R minus RO. Where I don't really know what R and RO are, to be honest. They might just be the same, R and RO. Let me see. Alright. Yeah. And that's equal to 0. Now, why is that the case? I don't know. But that's just the vector form of this. Yeah, I don't really use this all that often. Use the, I don't know what the standard form of a thing. So basically saying a vector n that is perpendicular, right? Let's see. Yeah, a vector n orthogonal to the plane and two arbitrary points R and O and R define a plane. Now, that represents what I was talking about here, but if we extend the logic, let me show time. Extend the logic of this and say this is ABC, which is vector n, and R is X, Y, Z. And we can do the same for the other side. Oh my. Alright, now. Alright, multiply, time, and then it's a minus XO. And then whatever. This is just RO. Right? I'm not gonna write all this, but basically A times X minus XO comma B times Y minus YO, etc., is equal to 0. And let me see this. Oh yeah, so it's not this. Okay, can't even cancel. Alright, anyways. So n, since this is they're both vectors, this must be the dot product, right? So A, B, C, if I remember, I showed you the dot product last time, and basically it's A times X minus XO plus B times Y minus YO, etc., right? So this would be A times X minus XO plus B, etc., equals 0. Now, the standard form for this would be AX plus BY plus C plus D equals 0, where D is equal to negative, and then A times XO plus B times YO, etc., whatever. So that is your standard form for a plane. That is how you define a plane. There you go. Yeah, that's all, I think. That's a lot of writing, but yeah. So key takeaways are: a plane can be made of two vectors, but typically you'd be using the normal vector of the plane, or the cross product of those two vectors, right? And because of that, you can define it as such right here, where R is X, which is anywhere on the plane, and RO is the point you picked on the plane. So N and R, well, N is unchangeable, R is the one changing, right? And RO is the random point you picked, or it's given. And yeah, so there you go. That's it.